Module 3, Lesson 7, Exponential Decay. Instructional outcomes: to describe and analyze exponential growth and decay models, and to solve problems involving exponential growth / exponential decay models. As always, the purpose of the videos here is to merely provide a resource for both the parent and the student so that both can review lessons at home and to improve classroom learning and provide improved homework understanding. So in example 1 of this particular lesson, we bring up this scenario about a young person named Malik who bought a car for $15,000. It goes on to state that as he drove it off the lot, his best friend Will told him that the car's value just dropped by 15% and that it will continue to depreciate 15% of its current value each year. So the question states, if the car's value is currently $12,750 according to Will, what will the value be in 5 years? And so the students are provided a table at this point to kind of get an idea of what goes on. So Will's statement said that the value dropped by 15% when it drove off the lot. So in order to find out the car's value after 2 years and the 15% depreciation in value, what we're asking the students to do is to take and multiply by 0.15, and that's going to equal how much is depreciated off of that value of the car. Then we'll take these two values here, the $12,750, we'll minus the $1,912.50, and that's going to equal this value. So in other words, this value here minus this value here is going to equal this particular value. And so then this value is carried over to here, and so if we want to know what 15% of that is, then we would multiply that $10,837.50 by 0.15 to get us the $1,625.63. We'll then subtract these two values and get the $9,211.87. So in pairs, the teacher is asking the student to take a few minutes, determine what it would be for 2 years, 3 years, 4 years, and 5 years. So if you haven't already done so, done this activity, go ahead and take a moment and pause it and try it in your book and see what you come up with, and then unpause the video when you have it. So if we continue to unveil the numbers, we have $1,381. Then we end up with a little over $7,800. And then I'll just reveal the remaining of these so you can check your answer of how these worked out each time. And so again, remember, just as a finalization, how did we get the $848.59? We multiplied this by 15 cents, and then we subtracted these two values to equal that value there. And so that is what the car's value will be in 5 years, $4,808.64. So this gave us students the opportunity, outside of a formula, of a geometric formula, to look at this depreciation each time as it continues to decrease. So here we're at this same table, and now we're asking the students to take what you learned and what you observed and write an explicit formula for the sequence that models Malik's car. Well, one thing that we do know is that the value of the car when he first purchased it was $12,750, $50.00. We know that it is losing value by 15% each time. So the formula goes on to say that we would want to do 1 plus r, the rate, but because of that, it's a depreciating value, it'll really be 1 minus 0.15. And so then if we take that out and simplify that, we end up with 0.85. And then that is raised to the t year, whether it be the first year, second year, third year, fourth year, or fifth year. And so in part C, it just says confirm your formula for part B. by determining the value of Malik's car after 5 years. So all they're asking that you take and do is take the $12,750 times the 0.85, plug a 5 up here for t to confirm that you do in fact get this answer here, and you will. Then it says in part D, use the formula for part B to determine the value of Malik's car after 7 years. So again, you'll just follow up. You'll do $12,750 times the 0.85 raised to the 7. And so when you simplify and solve for that, you'll end up with $4,087, $4,087.36. Again, just a note before we move on past this slide, that where did the 0.85 come from? Remember, it's the ace of 1 times the 1 plus the r raised to the t power. The 0.85 came from doing 1 minus 0.15, and the reason why we're minusing 0.15 is because we are depreciating in value. We're going down rather than increasing in value. So in exercise number 1, the students have an opportunity to do a think, pair, share, and they had to decide whether they believe something is an exponential growth or an exponential decay. And so the teacher is going to give them a bit of a definition to think about, an idea that we're going to look at the values that are inside the parentheses. They will fall into one or two categories. So if we look at these 5 values, the value is either going to be greater than 1, or it's going to be between 1 and 0. And so if that's the case, one of them is going to define a growth and one of them is going to define a decay. If it is greater than 1, then it's going to define a growth, and if it is less than 1, it's going to define a decay. So if we look at the values and kind of look at them here, here is 2 to the 2/5 power, where 2/5 power is less than 1. And so that will end up being a decay. If we look at this one here, 5/3, 5/3 is a growth, so that will move here. A 3 is greater than 1, so it will grow to over here. 1/3 is a decay, and then 2/3 is also a decay. So again, that's kind of the general idea that you want to look about. You want to look at that number that is the base for the exponent t. And if it's greater than 1, it'll be a growth. If it is less than 1, it'll be a decay, looking at that particular perspective. So in exercise number 2, we're going to look at a few word problems starting at this point as to what an exponential decay formula looks like and what does it do over the course of time and so forth. So it says if a person takes a dosage D of a particular medicine, then we are given a formula of f of t is equal to d times the 0.08 to the t power. Represents the concentration of the medicine in the bloodstream t hours later. If Charlotte takes 200 milligrams of medication at 6 a.m., how much remains in her bloodstream at 10 a.m.? And then it goes on to say how long does it take for the concentration to drop below 1 milligram. So if this is the formula, so we have our f of t equals the d, which is going for us going to be 200, times the 0.8, and we're going to raise it to the t power. They say we took the medicine at 6 o'clock, and we want to know how much remains at 10 o'clock. Well, that is 4 hours later, so we would place a 4 in this position, simplify this, and we will end up with 8 f of t will equal 81.92 milligrams would be left in our particular system at that point in time. And the follow-up question is, how long does it take for the concentration to drop below 1 milligram? Well, at that point, the students will kind of experiment with it. They would look at this particular 4 and say, well, you know, after 4 hours we had the 81.92. And so students might start trying different values. They might try the 5 or the 6 or the 7. They might start to jump a little bit quicker and try different things. Ultimately, the students are going to find out that if I want to drop below 1 milligram for the first time, then I will ultimately end up needing this particular piece here, the 0.8, and I'll have to raise that to the 24 hours. So about 24 hours later, after that case, I will have 1 milligram of this in my system. In exercise number 3, it says when you breathe normally, about 12% of the air in your lungs is replaced with each breath. Write an explicit formula for the sequence that models the amount of original air left in your lungs, given that the initial, that's a key word, the initial volume of the air is 500 milliliters. Use your model to determine how much of the original 500 milliliters is remaining after I take 50 breaths. So again, we look at our formula, the a sub 1 times the 1 plus the rate raised to the t, or the breaths in this case, that we take. So initially I have 500 milliliters of breath. I have my 1, now this is going to be a loss or a depreciation of air, so a minus 0.12 for breaths, and they want to know after I take 50 breaths. So if we look at the 0.12 and we subtracted that, so the 1 minus the 0.12, so I end up with 500 times 0.88 raised to the 50th power. So once you solve that and calculate that after 50 breaths, we end up with only 0.83 milliliters of the original 500 milliliters of breath that we began with at the beginning of this particular problem. In exercise number 4, Ryan bought a new computer for $2,100. So there's our initial value. This is going to be kind of like the car that we bought at the beginning of this lesson. It says the value of the computer decreases by 50% each year. When will the value drop below $300? So again, what would the formula look like? Well, initially I've got $2,100 worth of computer, but then it decreases by 50%, so 1 minus 0.5, and that's going to be raised to the number, to the t value, because we're talking about years. So 2100 times 0.5 raised to the t power. Now it's also possible students are going to notice here that if we're talking about t equals 0, that's when I bought the computer, it was worth 2100. And they're going to say, well, Mr. Acord, or whatever, I don't need to use this formula because I know that 1/2, that each year is going to drop by 1/2. So if I do 2100 divided by 2, then I know after 1 year, my computer is only going to be worth $1,050. If I go 2 years, so I'll divide that by half again, I'll end up with it being worth $525. And so year 3, if I divide that by 2, I end up with $262.50. And so we'll see after year 3, it will drop below $300 in value for that particular computer. Again, and this can be confirmed. If I was to take this 2100 and raise that to the 3rd power, I would still get my $262.50. The final example that we're going to look at together is exercise number 5. It says Kelly's mom takes a 400 milligram dose of aspirin. Each hour, the amount of aspirin in the person's system decreases by 29%. How much aspirin is left in her system after 6 hours? So again, following the idea that we've been looking at, the original value, we've got the 1 plus the rate raised to the t power. Well, we started with 400 milligrams. We are going to decrease by 29%, or 0.29 every single hour. So if I did 1 minus 0.29, I'm going to get 400 times 0.71 raised to the 6th power. Why to the 6th power? Because we want to know how much is in our system after 6 hours. So if I do my 400 times my 0.71 and I raise that to the 6th power, then I'm going to get approximately 51 milligrams left in my system after 6 hours.